but I'm scared. I don't know how deep this pool is.
Hold on. Let's use this stick to check the depth of the pool. Can you see that its length is bigger than you?
Let's put it in the pool.
Okay. See? Half of the stick is outside. So you can go inside. It's not very deep.
But look, Ginny, the stick looks bent.
Yes, that is not bent. This looks bent due to refraction of light.
Refraction? Oh, you told me about reflection, but you never said anything about refraction. What is refraction?
You know, when light travels from one medium to another, it bends.
Like when it moves from air to water, one medium to another?
Yes, air is one type of medium and water is another type of medium.
Hey, even your hand looks bent.
Yes, and now you know that it seems bent due to refraction of light.
But why does light refract?
For that, you first need to enter the pool.
But why?
Go on, young man. To learn something, you need to do something.
Okay. This water is so cold. I want to come out.
Okay, but before you come out, try to run for some distance in the water.
I can't run faster. This water is stopping me.
Darling. Now come out. Let's go home and learn more about refraction. So Jimmy, you could not run fast in water, correct?
Yeah, I can run much faster otherwise.
Let's see. Why could you not run fast in water? You know, water is more dense than air. You have to run against air while on ground. But your speed is less in water because the water is denser than air.
So, same thing happens to the light. When it enters water from air, its speed becomes less and its direction changes.
More magic now, making the handle of a pirate's kitchen jug disappear. Never know, might come in handy someday. Maybe. The power of invisibility, it's not just the stuff of science fiction and superheroes, it's a reality. This is the handle of a pirate's jug. It's perfectly visible, right? But watch what happens when I add some vegetable oil. Well, the handle's disappeared. The reason this happens is because light refracts. Light moves at different speeds through different substances, and this speed is measured by something called refractive index. When light travels through two substances with different refractive indexes, it changes direction at the boundary between these two substances if it's traveling at an angle. This can be seen here by shining a light through a glass block. This change in direction is called refraction. Refraction makes looking at objects underwater quite tricky. This is because water and air have different refractive indexes. The light from objects underwater changes direction when it leaves the water, making them appear in a different place to where they actually are. Diving birds have to make adjustments for this when looking for fish. An object is only visible if it reflects or refracts light. When the glass is empty, the handle of the jug is visible because the air in the glass has a different refractive index to the Pyrex.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
This magnifying glass is making my eye look big. Now, why is that?
I don't know.
Please consider the following.
Okay.
When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are three straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction so that they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Oh, look, over here the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Ha! Thanks for joining me on Consider the Following.
그댈 향해 걸어가는 사랑해요 그대 고마워요 항상 잊지 말아요 함께 웃어요 그대 위해 살아가는 사랑해요 그대
And so when light moves from one medium to another, it can be reflected, absorbed, or transmitted. Now in this video, we're dealing with light that is transmitted into that other medium. Now in this example, however, the light came in at a straight angle, and so we don't see that refraction. But what happens if it comes in at an angle that is not along the normal or not along the perpendicular? And so these are the two mediums. This is the one on the left and the one on the right. This would be the boundary between the two, and then this is the normal line right here. And so what happens if it comes in from one medium, enters another medium where it's going the same exact speed? There's going to be no change in the angle. It's just going to go straight through. Just like light goes straight in air because the medium is never changing. What happens, however, if it goes from one medium to another, and that second medium, it actually travels slower? As it does that, it'll actually bend towards the normal, or it's going to bend towards that dotted line or the perpendicular line. I'll give you an analogy that'll help you to remember that. What happens if it comes in and it's moving into a faster medium? It'll actually bend away from that normal. So it's going to bend like that. Now that's called refraction. We see the bending of the light, and we can actually quantify that using something called Snell's law. Snell's law, to quantify it, we have to add a couple of different variables. We first of all have to define this as the angle of incidence and this as the angle of refraction. Again, we're always measuring the angle between the normal and the light ray itself. And then we have N1 and N2. So this is what the formula for Snell's law looks like. And so the index of refraction, we call that N1, on one side times the sine of the angle equals the index of refraction on the other side times the sine of the angle of refraction on the other side. And so we can actually figure out what angle it's going to bend at if we know a little bit about the speed at which it's going through. And we also, if we see the bend, we could figure out the speed at which it's going through as well, because the index of refraction is equal to the speed of light divided by the velocity. Now, if we take that angle and we start to increase it, increase the angle of incidence, we eventually can reach what's called a critical angle. And instead of being refracted, it will not be refracted. It'll just go straight along the margin. And if we increase it above the critical angle, then it's going to be reflected into that first medium. And so what happens is eventually, if you get the angle right, you'll have total internal reflection. None of it is being refracted or transmitted through that boundary.